Right, in this lesson, we shall solve this question 7. Use the figure below to prove the theorem that states the line drawn from the center of a circle perpendicular to a chord bisects the chord. The question is, how do we prove this result? So first and foremost, we need to note that we are required to prove that RTP, required to prove that PM is equal to MQ. Supposed to prove that we're required to prove that PM is equal to MQ, because we're saying the line drawn from the center of a circle, right, perpendicular to a chord bisects the chord. So this line here, that is from the center of a circle to a chord, bisects the chord, so it divides this chord into two equal parts. So to do that, we perform a construction. Right, we perform a construction. What is this particular construction? So we then proceed to draw. Right, we draw radii. We draw radii OP and OQ. Right, we draw radii OP and OQ, like so. Right, we draw the radii like so. So draw radii OP and OQ. And now we proceed to present the proof. We present the proof. How do we present the proof? Right, so in the way we present the proof, we're going to say in triangle. We state the triangles, so in triangle OPM and triangle OQM, like so. We mark a couple of points that we shall be stating, like the first point. What is the first point? Right, so we attempt to prove that this triangle and that triangle are congruent triangles. So now to prove these triangles are congruent, we seek to identify sides and angles that are equal in the two triangles. For example, right, you are able to see that OP and OQ are radii. So OP, we see that OP equals OQ. Why? They are radii. Okay, so that is what we are able to see. So OP equals OQ, they are radii. 2, we're able to see that OM equals OM. And this is a common side. So we're able to see that OM equals OM, common side. Third point, we're able to see that angle OMP, angle OMP, okay? Right, so angle OMP is equals to angle OMQ, and this is equal to 90 degrees. Right, so angle OMP is equals to OMQ equals 90 degrees. Why? Well, this is given. It is given that angle OMP and OMQ are the same. Therefore, triangle OPM is congruent to triangle OQM. Why? Why are these triangles congruent? Right, these triangles are congruent because you have a right angle, you have a hypotenuse, and you have a side. Right angle, hypotenuse, and a side. By the RHS, we mean that you have a right angle. All right, we have a right angle, we have a hypotenuse. Right, we have a hypotenuse, but we also have a side. Right, so we have a right angle, we have a hypotenuse, and a side. Okay, so that is what we have. So when these two triangles are congruent, the couple of things, therefore, that remain extremely, extremely important. What then becomes very, very pertinent? It becomes very pertinent for us to then observe that hence PM equal to MQ. Hence PM equals MQ. Right, so we're able to see that PM and MQ are equal to each other. They are equal to each other. So we are excited about this. They are equal to each other. Right, so we're excited. We are very, very excited. Okay, all right. Any question about this proof? So because we were required to prove, the RTP is required to prove, so we're required to prove that PM equals MQ. But you see, the way the examiner structured the question, the examiner said, use the figure below to prove the theorem that states the line drawn from the center of a circle perpendicular to a chord bisects the chord. And now to prove this, we are required to prove that PM is equal to MQ. How do we then prove that PM is equal to MQ? We perform a construction. We draw radii OP and OQ. And that is what we did. We drew radii OP and OQ. And then now we proceed to present a proof to this. The proof is we state, and very important, we state and we tell the examiner, Mr. Examiner, we are going to be working in triangle OPM and triangle OQM. Okay, so we're going to work in these two triangles. We're going to attempt to use the grade 10 property. Grade 10 property. What is the grade 10 property? The grade 10 property is the property that is about the congruent triangles. Right, so two triangles are congruent, and we want to prove that they are congruent. But first things first, right? OP is equal to OQ. OP equals OQ, which is radii. OM equals OM, which is a common side. OM equals OM, which is a common side. Right, moreover, we have OMP equals OMQ equals 90 degrees. These are given because we were told that the line drawn from the center of a circle perpendicular to a chord. We're told that this line here is perpendicular to a chord. Because this line is perpendicular to a chord, then it becomes basically such that it makes angles of 90 degrees on either side. So now, obviously, because you're told that this line here is perpendicular to the chord, so it makes angles of 90 degrees on either side. Okay, now the couple of things then that become key to this. What then are we able to observe, moreover? We are able to see that at this point, OM equals OM a common side, and therefore, obviously, we have the angle here 90 degrees, and also this one here is an angle of 90 degrees. Okay, and therefore, we're able to make a conclusion that therefore, the triangle OPM, this triangle here, is congruent to the triangle OQM, and the reason for that is RHS, right angle, hypotenuse, and a side. Okay, there's an angle of 90 degrees, a right angle, there's the hypotenuse, and the side OM in each case, and therefore we have that these two triangles remain very, very congruent. Now, there are a couple of things that we shall continue to do, and the next thing is to try and solve the next problem. Let us solve the next question. Right, here comes the next question. AB is a chord in circle. Right, AB is a chord in circle. Right, AB is a chord. Here is the AB. AB is a chord. And we can see this chord here. The center is O. OC is perpendicular to AB. Right, we can see that OC is perpendicular to what? To AB. It is perpendicular, and it makes an angle of how many degrees? Of 90 degrees there. If AB is equal to 10, right, AB is equal to 10 centimeters, right, so you can be able to see, therefore, that AB equals 10 centimeters, right, so AB, which is this one here, is 10. It is 10 centimeters. OA is 13, right, so OA is what? It's exactly 13. Now, let's see this. So this one is 10 centimeters, and we are able to see that OA is 13 centimeters. Calculate the length of DC. Right, we just need to find the length of what? Of DC. This is similar to the question we did earlier. And we proceed to look at this question. This question, please, it's seen at grade 12, it's seen at grade 11. So grade 11s and grade 12s, take this question very, very seriously. We just want to find DC. So we are saying calculate the length of DC in other words. DC equals a question mark. We are saying what is the length of DC? Let us see what we can do here. Right, let us see what we can do here. All right. So now, what do we do first in an attempt to actually prove this? Right. First and foremost, we're able to see that AB is equal to 10 centimeters. Why is AB equals 10 centimeters? It was given to us. Okay, we're given that AB is 10 centimeters. So if AB is 10 centimeters, what do we then have? We have that because now this is perpendicular, it means that AD is equal to DB. It means that AD is equal to DB is equal to 5 centimeters. Why? Okay, so the reason for that is because OC is perpendicular to what? You can say OC is perpendicular to AB. That is the reason. If we don't want to state that reason, we will actually state another reason. And we can alternatively say here, perpendicular from center to chord bisects chord. Okay, we just have proven that perpendicular from center to chord bisects chord. Okay, so that in the end, then this is exactly 5 centimeters. This is 5 centimeters. Now, at this point, we have a triangle like this. So if you have this triangle that is going to be like this, going up and being extended like this here, this one is exactly 13 and this one is 5. And now we are just interested in finding, for example, the length of what? The length of DC, which is that little bit here, this little bit. And the question then is, how do we proceed to do that? Let us continue to actually analyze that together. If there's anything we realize is that OA is equal to 13 centimeters. OA is 13 centimeters and why is OA 13 centimeters? Because this one here was given to us. Right, it was given to us. So we were given that OA is 13 centimeters. All right. And what else are we able to see from there as a consequence? Right, we're able to see, therefore, that OD must be how many centimeters here as a consequence? OD must be how many centimeters as a consequence? Right, so to find OD, because we just need to find this little bit here. We need to find this one. And to find that one, we need to use Pythagoras theorem. So we're going to proceed to then say OA squared. Right, OA squared is equal to what? Okay, let us do it carefully. So we can see that we have OA squared is equal to OD squared plus AD squared. Why? OA squared is equal to OD squared plus AD squared. And the reason for the squares, why are we just squaring everything here? This is called Pythagoras. Right, it is Pythagoras. So as a consequence, which means that you have 13 squared is equal to OD squared plus the AD is 5 squared. Okay, so what is the answer to this? Which means that OD squared is equal to 13 squared minus 5 squared. What is 13 squared minus 5 squared? Okay, right. So 13 squared minus 5 squared is actually 144. This is like 169 minus 25. You can write those steps down. So 13 squared, we know very well, is 169 minus 25, and this is 144. And this means that you take the square root of OD squared, and you take the square root of 144, and therefore, as a consequence, you have OD is equal to 12 centimeters. Right. And once we're able to get that OD is 12 centimeters, so we come here and you can see that this OD here, so OD is equal to 12 centimeters. If OD is 12 centimeters, this whole radius, what is the whole radius? The whole radius is 13 centimeters. Right. So this one must be 1 centimeter. And this one is 12 centimeters. This one is 12. So this one must be 1. And therefore, as a consequence, we're able to make the following conclusion and say hence. Right, we're able to say hence DC, which is what the examiner wants. We said find the length of DC. We're able to see that DC is equal to 1 centimeter. Why is DC equal to 1 centimeter? It is equal to 1 centimeter because in the end, then we have 1 centimeter plus 12, which is what? 13 centimeters. 13 centimeters. Okay, so yeah, that is what we have. So which means that hence DC is 13 centimeters. It is 13 centimeters there. Okay, and we have been able to do this question. Think about it, people. Make sure you understand this very, very well. Make sure you understand this question very, very well. Okay, it was said for the FET phase students at grade 11 and grade 12. Okay. Let's look at this one. Okay, AP is the diameter of circle center O. So we can see that at this point, we have that AP is a diameter. So what is the diameter? A diameter is in the first place a chord. It is a chord that passes through the center of the circle. Chord BC. Chord BC bisects angle DCP. Chord BC bisects angle DCP. And PA is perpendicular to BC. Right, we have that PA, right? So we have that PA is perpendicular to BC, like so. Right. Okay, so and here are the questions. Find 5 angles equal to BCP, equal to BCP. And we need 5 of those angles. Right, let's get cracking, everybody. Right, so now let us find those angles. So first things first, we note that angle ACP, because now this one is a diameter. So in mathematics, a diameter like this will always subtend an angle of 90 degrees. So in mathematics, if you have a circle like this, and somebody tells you that the circle has a center and there's a diameter, it will always subtend an angle of 90 degrees at the circumference of the circle. Right, so this angle is always 90 degrees over there. Okay, so that we're able to see that angle ACP is equal to 90 degrees. What is angle ACP? It is 90 degrees because it is subtended by a diameter. Why? We say the reason for this, we say because it is an angle in semicircle. Right, angle in semicircle. The Americans, the British say angle in semicircle, and the Americans say angle in semicircle, the Americans. Okay, but the same thing is implied. So to do this successfully, let us proceed to let, because we want to deal with the angle BCP. So BCP, this one here. So let us let this very famous angle for this question, let us call it X. So we let this angle to be equal to X. This angle BCP, we call it X. Why are we calling this angle X? Right, so we let it to be X. Okay, if we let it to be X, let's find the angle. So in other words, we come here. We come here. And when we come here, we're going to call this angle X. Right, we're going to call this angle here X, this one. Okay? And once we call it X, let us think. Now, there are a couple of angles that are very important. So there's a bow tie theorem, like a bow tie, because there is this one and there's this one. The angle here is the angle here. The angle here is the angle here. Okay, this is like the bow tie theorem. So if you have if these points lie on the circumference of a circle, then you know very well that the angles are equal to each other. This equals this and that equals that. So now we have the angle BCP. Right, so we have the angle BAP. So like if you look at this one here, right, you're able to see this one going down, but also this one here and this one here, like this. Okay, so sometimes the figure can just be like this, and you have this with this, and then you have this with that. They're just sitting like that, so that this one and these are the same. And that is what is happening here, because this one here is equal to that one there. So this one here, BAP, is also X. So that angle BAP is equal to X. Why? Angles subtended by BP. Angles subtended by BP. If you don't want to say these are angles subtended by BP, that is why these angles are equal to each other. You can say that they're angles in same segment. You can say the angles in same segment. Okay, right. Now, what next do we do now? We're able to see that this one is equal to this here. So BAP is equal to X. Next, what about angle ABO? Because this one is X. In mathematics, if you have a triangle like this, such that this side equals this angle is going to be equal to that angle there. So if this one is X, that one is going to be equal to what? This one is going to be equal to X. So that in the end, then you have that angle ABO. ABO is also equal to X. Why is angle ABO equal to X? Because this line from the center to the circumference is called the radius, and that is called the radius. So in other words, we have that ABO is X, right? This angle is X, and that is also X. Why? Because you have radii OA equals OB, right? Or you can continue to say these are angles opposite equal sides. Angles opposite equal sides. Okay, now there are a couple of things that are important here. Okay, so now we have seen that this equals X and that equals X and also that equals X, but we can find more, like the angle DCB, right? Angle DCB. This angle DCB, this one, is also X. So the angle DCB is also X. Why is angle DCB equal to X? Angle DCB is X. Why? Why is it X, this angle here? Right, it is X because the chord, okay, check this reason here. Because the chord BC bisects, right? The chord BC bisects DCP. Because the chord BC bisects the angle DCP. Right, so you have been told that the chord here, the chord BC, this one, the chord BC bisects angle DCP. So it splits this angle DCP into two equal parts. So this part here is X, and that one is also X. X, this one, that one is also X. Next. There's another angle DAE. Angle DAE. Let us check angle DAE. DAE. Angle DAE is also X. Why is angle DAE X? This one here. Why is that angle DAE X? Right, you need to look at this and look at it very, very carefully. You need to look at this and look at it very carefully, because this angle here is equal to this angle there. There's a theorem. What does the theorem say? Let us reason together. There's a theorem. And the theorem says that it is a grade 11 theorem, but the matrix need to know it. Right, so you have a cyclic quad like this. This angle here is equal to that angle there. The exterior angle of a cyclic quad, exterior angle of a cyclic quad equals the interior opposite angle, and that becomes the reason. Right, so the reason for this is that the exterior angle of cyclic quad A, B, C, D. Exterior angle of cyclic quad A, B, C, D. So the exterior angle of cyclic quad A, B, C, D is equal to the interior opposite angle there. Okay, next. Next. We're interested now in also finding another angle. Let us check angle PAC. Right. PAC. What is the angle PAC? Right. So we can see that the angle PAC, this one is also X. The angle PAC is also X. Why is the angle PAC also X? Right, it is also X because of the sum of angles of the triangle PAC. The sum of the angles of the triangle PAC. Right, because we remember that this one is 90 degrees. This one is X. So if you know two angles in a triangle, you can find the third one because they must add up to 180 degrees. So this one can only be 90 degrees minus X. So that when you add X minus X is 0, and then you have 90 plus 90, which is 180 degrees. Right. So now, once you get to this point, you think and think very carefully and then say, what is the size of this particular angle? For instance, let us check the angle PAC. Right, PAC is equal to what? So at this point then, if you know that obviously this angle here is X, and this angle here must be such that therefore when you add this angle, and also, but this one is the diameter, right? This one is a diameter. We have been told that here AP is a diameter of circle center O. If it is a diameter, this angle is 90 degrees. This angle is 90 degrees. So if it is 90 degrees, this angle, then this one is X. And you add everything, you get X minus X, which is 0. 90 plus 90 is actually 180. So the angles here would give us actually 180 degrees. So it means, therefore, we can confidently be in a position to also say angle PAC is actually equal to 90 degrees, is equal to X, excuse me. Okay, let us write that one down here. So we're going to write that one is our last point, right? So we are able to see that angle PAC is equal to X. Why is angle PAC equal to X? Because of the sum of angles of triangle PAC. Sum of angles of triangle PAC. Sum of angles of triangle PAC, when you add all of them, you get 180 degrees. This one here. Okay, and this here has given us a lot of the angles equal to X, equal to X, equal to X. So we let this one be X. So we found so many of them. We're supposed to find 5 angles equal to that. So in other words, now we found 1 here, 2, 3, 4, 5. Okay. And we found 5 altogether, 5 angles equal to BCP. Give reasons for each, and we have just done that. The diagram doesn't look very tidy, but yeah, we made the effort and we have got the answers there. Let us move on to the next question. Next question. Given circle with center O and points D, E, F, and G, right, points on the circumference. Okay, center O and you have D, E, F, and G points on the circumference. Prove that D plus F is 180. D plus F is 180 degrees. Okay, how do you prove that D plus F is 180 degrees? Okay, in other words, to begin the proof, we start the proof as follows. We say that we are required to prove that angle D plus angle F is equal to 180 degrees. Okay, so yeah, this we omitted. So we're supposed to prove that angle D, this one here, plus this one here, angle D plus angle F is 180 degrees. Let us look at what we need to do. And how do we prove this? We perform a construction. We perform a construction. Right, how do we perform this construction? We draw. Right, we draw radii. We draw radii EO and OG. We draw radii EO and OG. We draw the radii EO and OG. We draw radii EO and OG. Let us look at the proof of this. Let us look at the proof of this. Right. So to look at the proof, you remember we did something similar, and we had a discussion earlier about this with the students earlier on at 4 p.m. Right. So now to prove this here, it's very, very easy. Let us do it like this. Let us do it as follows. You can give them names. I mean, you can call this one 1 and call this one what? 2. And then you come and then say, for example, O1. Angle O1, this one, is twice angle F. Angle at center. Angle at center equals 2 times angle at circumference. What about angle O2? O2 is twice angle D. Angle O2 is twice angle D, which is angle at center, equals 2 times angle at circumference. Okay? And therefore now we have angle O1 plus angle O2 is 360 degrees, which is the angles around a point. Angles around a point. So we then say that O1 plus O2 is 360 degrees, angles around the point. So angle O1 we know very well is twice F. So angle O1 is twice F and angle O2 is twice D equals 360 degrees. Okay, we agree that at this point, if you have twice F plus twice D equals 180 degrees. So what we then do is we divide by 2. So, or we take 1/2, multiply by 1/2 left and right. So you have twice F, twice D, and we multiply 360 by 1/2. And then the implication of this is, obviously, this pointer is that angle F plus angle D is equal to 180 degrees. So we have been able to prove that F plus D is 180 degrees. And similarly, you can write it as they gave the things here. You can start in here and say this is angle D first plus angle F, just to write them in the order they gave up here, so that angle D plus F is 180 degrees. So we have proven these, guys. Take note. Okay, now, how do you learn this? You repeat. You watch the video. I'm gonna send you this video because this lesson is being recorded. So you watch the video, you pause the video at the end, you see if you can do it on your own without watching the video. If you cannot do it, you watch the video and you solve the problem again. That is what you need to do, because tomorrow we're going to write a test. I'm going to give you a test tomorrow, right, on these things. So you must be ready for the test for tomorrow, right, because the test is coming, and I'm expecting people to pass the test. Right, given circle O with with center O and points D, E, F, and G, points on the circumference, we have this diagram here. Deduce that CDE equals angle CDE. Angle CDE, this angle here, is equals to this angle here, angle F. So you need to deduce that angle CDE is equals to angle F. So the question is, how do we deduce this one? How? How do we deduce this one? Very, very straightforward. Who can deduce this one here? Okay. Now, there are a couple of things that remain very, very important, because we need to deduce. What is to deduce? Anyone quickly? What is to deduce? Anyone quickly? Okay. Now, we need to note that angle CDE plus angle EDG is equal to 180 degrees. Angle CDE plus EDG equals 180 degrees. Why? Because CDG is a straight line. Straight line. Okay, straight line. Okay. Straight line. So yeah, we have this. Next, if you have angle EDG, okay, angle EDG is this one, plus angle EFG is 180 degrees. And this is true because you have opposite angles of cyclic quad. Opposite angles of what? Of cyclic quad. So, okay, because this is 180, 180, which means therefore CDE plus EDG is equal to EDG plus EFG, like that. So that now we are able to see that EDG is available both sides and it cancels out, so that we are left with the CDE is equal to EFG. Okay, and obviously the EFG is just F. And this means that CDE is equals to angle F. Right, so which means that CDE is equals to angle F, which is what we're supposed to prove there. Okay, so obviously at this point, the fact that angle CDE, this one here, we add to angle EDG, we add to this one here, and you get 180 degrees. Because CDE is a straight line, CDG is a straight line. But also EDG plus EFG is 180 degrees, opposite angles of cyclic quad. Because obviously now this is equal to 180, this is equal to 180. So it then means, therefore, that these things here are equal to each other. Okay, so we continue. We continue. Right. And then now we have been able to prove this result here. Let's see what next is there to do for us. Okay, we have more to do. We have more to do. Right, we have this particular question to do. Okay, we have this particular question to do. So let's continue now. Let us do this one. Let us do this one. Right, so to do this one, there are a couple of things that are very important. In the diagram below, two unequal circles intersect at A and B. Two unequal circles intersect at A and B. AB is produced to C. Right. AB is produced to what? To C. Okay, and such that CD is a tangent to the circle ABD. So you have that CD is a tangent to the circle ABD. Right, ABD, we have that CD is a tangent. F and G are points on the smaller circle such that CGF and DBF are straight lines. Let's look at obviously CGF. Right, then you have CGF and you have DBF are straight lines. AD and AG are drawn. You have AD and you have that AG are drawn. Right, so we continue. Now you need to prove that angle B4, this one here, you need to prove that angle B4 is equal to angle D1 plus D2. Angle D1 plus angle D2. First things first, we're able to see that the angle B4, right, we're able to see that angle B4 is equals to angle B2. We're able to see that this angle B4 equals this. Because we're taught in primary school that this angle here is equal to this angle. What is the reason for this? The angles that are sitting like this around X. What do we call this here? Okay, what do we call those angles there? So these are vertically opposite angles. So B1 equal B4 equals B2. But B2, angle B2 is equal to D2 plus A plus A1. Angle B2, because at grade 10 we were taught this theorem here. If you have this angle here, if this is A, B, C, and this is 1, for instance, and this is 2, you know that angle C1 is equal to angle A plus angle B. So we continue. Right, so B2 is equal to D2 plus A1. Why? Because this one, C1 is equal to A plus B. Why? Because the exterior angle of cyclic quad equals the interior opposite angle. So we say that exterior angle of cyclic quad equals interior opposite angle. So we continue. Next, what else do we have here? For example, we know that this CD is a tangent. So the Chord theorem applies here. So the Chord theorem tells us that if you have something like this, if you have a tangent to a circle, the angle it forms with the chord equals the angle in the alternate segment. So you have this here like this. So this angle here is equal to that angle there. So at this point, this angle here between the tangent to the circle and the chord equals the angle that this chord is making. So this chord here makes an angle at the circumference of the circle. So this angle is equal to that angle there. So in other words, angle D1 equals, so yeah, first things first, let us write this one. So we're able to see that angle B4 equals B2, but B2 is this, so which means that B4 is actually equal to angle D2 plus angle A1. But we're able to see that but angle A1, or we can start with D1 as usual. It's normal to start with D1, right? So, but angle D1, this angle here, is equal to the angle A1. Why? Because this one is because of the Chord theorem. Chord theorem. And now we continue to solve more problems. Okay, but in other words, in the place of A1, we can put A1 is equal to D1. So which means that hence we're able to see that the angle before is angle D2 plus angle D1. So yeah, this one is D2 plus angle D1, and then you can write or you can write properly in the right order as the examiner gave, and then say it is exactly angle D1 plus angle D2. Right, which is angle D1 plus angle D2. And then now we have proven that angle before is equals to angle D1 plus angle D2. Okay, next question is to prove the second part of this. Next, we need to prove that this part. So we need to prove that AGCD is a cyclic quad. Here is A, here is G, here is C, and here is D. Want to prove that AGCD is a cyclic quad? How do we prove that AGCD is a cyclic quad? Right, so to prove that, we prove it with ease. All right, so the couple of things now, here is the shape, this one here. AGCD, this one here. AGCD, and this one here. Right, so something very important, you then say angle G2, this one here, is equal to what? Okay, it's like a butterfly, this. It's like a butterfly because, or it's like a bow tie, okay? These kinds of things, this theorem, okay? This angle is equal to this. Okay, and then we say that these are angles in same segment. Angles in same seg. Okay, angles in same segment, but also this one equals this one. Okay, so that now G2 is equal to B2. G2 is equals to angle B2. Right, so G2 equals angle B2, and what are we going to say? G2 equals B2, and these are angles in the same segment. These are angles in the same what? In the same segment. Angles in same seg. Right, we have angles G2 equals B2. These are angles in the same segment. Right. Moreover, what then do we have here as a consequence? Right, we have therefore that but angle B2, because now this is like this, is exactly like this. We're back to grade 10. Once you see this here, we're back to grade 10, because if you have CAB and then you put 1, 2, then you're going to say angle C1 is equals to angle A plus B. So that now you can then say angle C1 is A plus B. So here we will say B2 is D2 and A1. So B2 is actually angle D2 plus A1. Why? Because the exterior. Right, so we have the exterior. Exterior angle of, right, exterior angle of triangle equals the sum of interior opposite angles. Now, this is what we have. So B2 is equal to D2 plus A1. So what then do we have here? So it means that G2, it means that angle G2 is angle D2 plus angle A1. Okay, because they're both equal to D2. Both equal to angle B2. Right, and once you prove that, once you have that angle G2, this one here is equal to D2 plus A1, and so you know that obviously at this point you can mention many things. Right, you can mention in particular, you can do it nicely. I feel that doesn't matter. Let me see, you can do it nicely. You can just use the fact that B2 is equal to B4. Let me just do it that way. It is much shorter. It's much shorter. It's a shorter proof. Right, so but G2 is B2, but yeah, we can actually, it's much shorter to then say angle B2 is equal to, because they're vertically opposite angles, those angles that we spoke about, like this angle is equal to this. So an angle here, angles in X like this. So you can just say B2 is equal to angle B4, because B2 equals angle B4, these are vertically opposite angles, okay? So that angle B2, B2 is B4, and this one is equal to B4. Okay, so G2 is equal to B4. So G2, yeah, so ultimately G2 is equal to B4. But what did we prove here? We proved that B4 is equal to D1 plus D2. So you can just equate these things. And then come here and then say angle G2 is equal to, because this is B4 and B4 equals this, which means that G2 is angle D1 plus angle D2. Right, which means that G2 is a D1 plus, so in other words, you have that G2 is D1 plus D2. And hence AGCD. Now, you have been able to establish that this angle here, G2, can clean this up, has become so dirty now. So, but we've been able to make certain observations. We've been able to see that the angle G2 is equal to this D1 and D2. Okay, So because of this, it therefore means that you can then come here and say hence AGCD is a cyclic quad. It's a cyclic quad. Why? Because we are able to see that this angle G2 is equal to D1 and D2, and the exterior angle of quad, right, of quad equals the interior opposite angle. And now this is a result that is true by it is the converse of the exterior angle of a cyclic quad. Right, so, or you can actually then say it is the converse of the exterior angle of a cyclic quad result. Cyclic quad. Okay, so you can say this. It is the converse of the exterior angle of a cyclic quad. Okay, just look at that and think about it very carefully and make sure that you have the understanding that is required. Okay. Now we proceed to do 9.2.3. Let's look at 9.2.3, which is this one. Want to prove that, so this one is very, very easy. We just want to prove that DC, here is D, and here is C. Want to prove that DC is equal to CF. Here is C and here is F. We want to prove that they're equal to each other. Now, there are a couple of things that are very, very important for us to sort of consider. Let's look at the bow tie. Okay, we remember this theorem here. This is the theorem. Okay, so this theorem is very important because this is equal to this. So, which means that at this point, we have what? Okay, so there are many things that we have here. And we're going to be very, very excited to prove this particular result. So let us celebrate. But first things first, we're able to see that angle D1 is equal to angle A2. Angle D1 is equals to angle what? Is equals to angle A2. Why is angle D1 equals to angle A2? Let us look at these very carefully. Okay, because these are angles because it's another bow tie, this one. Because you already know that this one is a cyclic quad, this. You already know that this one is what? Is a cyclic quad. Okay, so yeah, up to this point. Okay, so let us look at this. Yes, so you can just trace it very well. Trace it carefully so that you have the right interpretation. Okay, this one that sits here, and you have this A2, for instance, because you have the G2 there, and you also have that the angle D1, which is exactly this here. Right, so able to see that this angle here is equal to most certainly that angle over there. And D1 is equal to the angle A2. These are angles in same segment. In same segment. Right, and once you note, therefore, that these are angles in the same segment, what more then can we be able to achieve out of these, right, we can be able to achieve many, many things. Right, we can be able to say that angle A2 is equals to angle F. Why is angle A2 equals to angle F? Right, angle A2 is equals to angle F because, let me just clean up to make sure that this is, okay, let's look at angle A2 and angle F here. Right, angle F is this one here. And you're looking at angle A2, which is this angle there. What are we able to see, for example? Right. So if you look very carefully and you see this angle here, and you see this angle here. So angle A2 is equal to angle F. They form like a butterfly or a bow tie. So angle A2 is equal to angle F, and these are angles in same segment. Angles in same sag. Right, so we have this, which means that angle D1 is equals to angle F. Okay, because they're both equal to A2. Okay, and therefore, as a consequence, it means that angle DC is equals to angle CF, which means that angle DC is equals to angle CF, because you've already shown that this angle D1 is equals to the angle F, so that we're able to see that rather segment DC, right? Okay, segment DC is equal to CF, which are sides opposite equal angles. Sides opposite equal what? Equal angles. Right, so these are the things that you need to look at very carefully and think about this to ensure that you are in a position to understand this very, very much. Okay, so yeah, get to think about this and ensure that you understand your geometry and are able to solve the problems. I think that we have been able to obviously conclude this result here. And right, go and watch these videos and practice these questions. Make sure that you're able to establish what is happening. Right, I think that for tonight, thanks a lot for joining us. I'm going to be sending this video in the next couple of minutes. Right, thanks for joining us. And yeah, I'm going to see you guys tomorrow at 4 p.m. For those who are busy at 4 p.m., we're going to have another lesson at 8 p.m. tomorrow. Every weekend, 4 p.m. and 8 p.m. Saturday is 4 p.m., 8 p.m. Sunday, the same thing, 4 p.m., 8 p.m. So yeah, I'm going to see you at 4 p.m. Tomorrow, Sunday afternoon. Okay. Right. For today, thank you. Thank you so much for joining us, and good night. Right. So